Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
Active information gathering. In this module, we'll explore techniques that involve direct interaction with target services. We'll look at some of the more common active information gathering techniques, including port scanning and DNS, SMB, NFS, SMTP, and SNMP enumeration. DNS Enumeration. DNS is the naming system on the Internet. It is a distributed database responsible for translating user-friendly domain names into IP addresses. When a browser needs to resolve a host name, like www.megacorp1.com, it passes the host name to the operating system's DNS client, which forwards the request to the external DNS server it's configured to use. The first server in the chain is known as the DNS recurser and is responsible for returning the results to the DNS client. The recurser queries the authoritative name server, which contains the DNS records in a local database known as a zone file. There are typically two zones for each domain. The forward lookup zone is used to find the IP address of a specific host name, and the reverse lookup zone is used to find the host name of a specific IP address. Once the DNS recurser provides the DNS client with the IP address for www.megacorp1.com, the browser can contact the correct web server at its IP address and load the web page. Interacting with the DNS server. Each domain can use different types of DNS records. Due to the wealth of information contained within DNS, it's often a lucrative target for active information gathering. To demonstrate this, we'll use the host command to find the IP address of www.megacorp1.com. By default, the host command looks for an A host record. But what if we wanted to find the MX, or perhaps some interesting TXT records? To do this, we can use the -T option to specify the type of record we're looking for. For example, to find servers that handle email for the domain, we search for the MX records. DNS text records can contain any type of arbitrary data and are often worth investigating. Automating lookups. Now that we have some initial data from the megacorp1.com domain, we can continue to use additional DNS queries to discover more host names and IP addresses belonging to the same domain. For example, we know that the domain has a web server with the host name www.megacorp1.com. Let's run host against this host name. Now, let's see if megacorp1.com has a server with the host name I don't exist. First, we queried a valid host name and received an IP resolution response. By contrast, our second query returned an NX domain error, indicating that a public DNS record does not exist for that host name. Now that we understand how to search for valid host names, we can automate our efforts. Forward lookup brute force. Brute force is a trial and error technique that seeks to find valid information, including directories on a web server, username and password combinations, or in this case, valid DNS records. By using a word list that contains common host names, we can attempt to guess DNS records and check the response for valid host names. In the examples so far, we used forward lookups, which requests the IP address of a hostname to query both a valid and an invalid hostname. If host successfully resolves a name to an IP, this could be an indication of a functional server. We can automate the forward DNS lookup of common host names using the host command in a bash one-liner. We will use this short list of potential host names for demonstration purposes. Our one-liner will loop through our list and attempt to resolve each host name. With this simplified word list, we discovered entries for www, mail, and router. The host names FTP, OWA, and proxy, however, were not found. Much more comprehensive word lists are available as part of the SecLists project, which can be installed with apt. Reverse lookup brute force. Our DNS forward brute force enumeration revealed a set of scattered IP addresses in the same approximate range. If the DNS administrator of megacorp1.com configured PTR records for the domain, we could scan the approximate range with reverse lookups to request the host name for each IP. Let's use a loop to scan IP addresses 50 through 100. We'll use grep-v to filter out invalid results by showing only entries that do not contain the not found message. We've successfully managed to resolve a number of IP addresses to valid hosts using reverse DNS lookups. If we were performing an assessment, we could further extrapolate these results and might scan for mail 1, mail 3, etc., and reverse lookup positive results. The point is that these type of scans are often cyclical. We expand our search based on any information we receive at every round. DNS Zone Transfers. A zone transfer is basically a database replication between related DNS servers in which the zone file is copied from a master DNS server to a slave server. The zone file contains a list of all the DNS names configured for that zone. Zone transfers should only be allowed to authorized slave DNS servers, but many administrators misconfigure their DNS servers, and in these cases, anyone asking for a copy of the DNS server's zone will usually receive one. This is equivalent to handing a hacker the corporate network layout on a silver platter. All the names, addresses, and functionality of the servers can be exposed to prying eyes. A successful zone transfer does not directly result in a network breach, although it does facilitate the process. The host command can be used to perform a zone transfer with the -L option, followed by the domain name and a DNS server. Let's begin by finding the DNS servers for megacorp1.com. This domain has 3 DNS servers, NS1, NS2, and NS3. Let's try a zone transfer against each one. We'll use host-L to attempt the zone transfers. Unfortunately, it looks like the first name server, NS1, does not allow zone transfers, so our attempt has failed. Let's try the same steps using the second name server, NS2. This server does allow zone transfers and provides a full dump of the zone file for the megacorp1.com domain. It delivers a convenient list of IP addresses and corresponding DNS host names. The megacorp1.com domain has very few DNS servers to check. However, some larger organizations might host many DNS servers, or we might want to attempt zone transfer requests against all the DNS servers in a given domain. Bash scripting can help with this task. To attempt a zone transfer with the host command, we need 2 parameters, a name server address, and a domain name. We can get a clean list of the name servers for a given domain with the host command, piping the results into cut. Taking this a step further, we can write a bash script to automate the process of identifying the relevant name servers and attempting a zone transfer from each. Our script will identify the name servers for the given domain and attempt a zone transfer against each one of them. Let's make the script executable and run it against megacorp1.com. Great. Just a few lines in a script has automated our task quite nicely. Relevant tools in Kali Linux. There are several tools in Kali Linux that can automate DNS enumeration. Two notable examples are DNSRecon and DNSEnum, which have useful options that we'll explore in the following sections. DNSRecon. DNSRecon is an advanced, modern DNS enumeration script written in Python. We can attempt a zone transfer with DNSRecon by using the -D option to specify a domain name and -T to specify the type of enumeration to perform, in this case, a zone transfer. We've managed to perform a successful DNS zone transfer against the megacorp1.com domain. The result is basically a full dump of the zone file for the domain. Let's try to brute force additional host names with the list we used previously for forward lookups. We'll use the -D option to specify a file name containing potential subdomain strings and -T to specify brute force enumeration. Our brute force attempt has finished, and we've managed to resolve a few host names. DNSEnum. DNSEnum is another popular DNS enumeration tool. To show a different output, let's run DNSEnum against the zonetransfer.me domain, which specifically allows zone transfers. We simply need to pass the domain of interest to DNSEnum. These enumeration tools are both capable and straightforward. Take some time to practice with each before continuing. Port scanning. Port scanning is the process of inspecting TCP or UDP ports on a remote machine with the intention of detecting what services are running on the target and what potential attack vectors may exist. Using a proper port scanning methodology can significantly improve our efficiency as penetration testers while also limiting many of the risks. Depending on the scope of the engagement, instead of running a full port scan against the target network, we can start by only scanning for ports 80 and 443. With a list of possible web servers, we can run a full port scan against these servers in the background while performing other enumeration. Once the full port scan is complete, we can further narrow our scans to probe for more and more information with each subsequent scan. The results of one scan determine the type and scope of the next scan. TCP UDP Scanning. We'll begin our exploration of port scanning with a simple TCP and UDP port scan using Netcat. It should be noted that Netcat is not a port scanner, but it can be used in such a rudimentary way. Since it's already present on many systems, we can repurpose some of its functionality to mimic a basic port scan when we don't need a fully featured port scanner. However, there are far better tools dedicated to port scanning that we'll explore in detail as well. TCP Scanning. The simplest TCP port scanning technique, usually called Connect Scanning, relies on the three-way TCP handshake mechanism. In basic terms, a host sends a TCP SYN packet to a server on a destination port. If the destination port is open, the server responds with a SYN ACK packet, and the client host sends an ACK packet to complete this handshake. If the handshake completes successfully, the port is considered open. Let's launch Wireshark so we can inspect our traffic. We'll set a capture filter so we only collect the traffic we're interested in. Now, let's run a TCP Netcat port scan on ports 3388 through 3390. The -W option specifies the connection timeout in seconds, and -Z is used to specify 0 IO mode, which will send no data and is used for scanning. Based on this output, we can see that port 3389 is open, while connections on port 3388 and 3390 timed out. Let's return to Wireshark and inspect our capture. In this capture, Netcat sent several TCP SYN packets to ports 3390, 3389, and 3388 on lines 1, 3, and 7, respectively. Due to a variety of factors, including timing issues, the packets may appear out of order in Wireshark. Notice that the server sent a TCP SYN ACK packet from port 3389 on line 4, indicating that the port is open. The other ports did not reply with a similar SYN ACK packet, so we can infer that they are not open. Finally, on line 6, Netcat closed down this connection by sending a FIN ACK packet. UDP Scanning. Since UDP is stateless and does not involve a three-way handshake, the mechanism behind UDP port scanning is different from TCP. Let's run a UDP Netcat port scan against ports 160 to 162 on a different target. This is done using the only Netcat option we have not seen yet, -U, which indicates a UDP scan. From the Wireshark capture, we can see that the UDP scan uses a different mechanism than a TCP scan. An empty UDP datagram was sent to specific ports in datagrams 1, 3, 4, and 5. If the destination UDP port is open, the datagram will be passed to the application layer, and the response received will depend on how the application is programmed to respond. In this example, the application sends no response. However, if the destination UDP port is closed, the target should respond with an ICMP port unreachable, as seen in datagrams 2 and 6, that is sent by the UDP IP stack of the target machine. Most UDP scanners tend to use the standard ICMP port unreachable message to infer the status of a target port. However, this method can be completely unreliable when the target port is filtered by a firewall. In fact, in these cases, the scanner will report the target port as open because of the absence of the ICMP message. We'll see later how dedicated scanners resolve this issue. Port scanning with Nmap. Nmap is one of the most popular, versatile, and robust port scanners available. Some of the Nmap example scans we cover in this module are run using sudo. This is due to the fact that quite a few Nmap scanning options require access to raw sockets, which in turn require root privileges. Let's explore some port scanning examples to get a better feel for Nmap and its options. Accountability for our traffic. A default Nmap TCP scan will scan the 1,000 most popular ports on a given machine. Before we start running scans blindly, let's examine the amount of traffic sent by this type of scan. We'll scan one of the lab machines while using IP tables to monitor the amount of traffic sent to the target. First, we'll use the IP tables -I option to insert a new rule into the input chain in the first position. -S to specify a source IP address, which is the IP address we're going to scan, and -J accept to allow the traffic to pass. We'll also add a rule to the output chain. This time, we specify output as the chain and use -D to specify the destination IP address. Lastly, we'll use the -Z option to zero the packet and byte counters in all chains. Now, let's generate some traffic using Nmap. We'll run a default scan by providing the target IP address without any other options. The scan completed and revealed a few open ports. Now, let's inspect some IP table statistics to get an idea of how much traffic our scan generated. We'll use the -V option to add some verbosity to our output, -N to enable numeric output, and -L to list the rules present in all chains. According to this output, the default 1,000 port scan has generated around 70 kilobytes of traffic. Let's zero the IP tables packet and byte counters in all chains again and run another Nmap scan. This time, we'll use the -P option to specify all TCP ports. In this port scan, explicitly probing all 65,535 ports, we generated about 4 megabytes of traffic, a significantly higher amount. These results imply that a full Nmap scan of a Class C network would result in sending over 1,000 megabytes of traffic to the network. However, this full port scan has discovered new ports that were not found by the default TCP scan. In an ideal situation, a full TCP and UDP port scan of every single target machine would provide the most accurate information about exposed network services. However, this example reveals the need to balance any traffic restrictions, such as a slow uplink, with the need to discover additional open ports and services. In the next section, we'll explore some of Nmap's various scanning techniques. Stealth SYN Scanning. Nmap's preferred scanning technique is a SYN or stealth scan. There are many benefits to using a SYN scan, and as such, it's the default scan technique when no scan technique is specified and the user has the required raw socket privileges. SYN scanning is a TCP port scanning method that involves sending SYN packets to various ports on a target machine without completing a TCP handshake. If a TCP port is open, a SYN ACK should be sent back from the target machine, informing us that the port is open. At this point, Nmap does not bother to send the final ACK to complete the three-way handshake. To launch a SYN scan with Nmap, we preface the command with sudo and provide the -S option. Because the three-way handshake is never completed, the information is not passed to the application layer, and as a result will not appear in any application logs. A SYN scan is also faster and more efficient because fewer packets are sent and received. Note that the term stealth refers to the fact that in the past, primitive firewalls would fail to log incomplete TCP connections, combined with the fact that application logs wouldn't catch the scan. TCP Connect Scanning. When a user running Nmap does not have raw socket privileges, Nmap will default to the TCP Connect scan technique described earlier. Since a TCP Connect scan makes use of the Berkeley Sockets API to perform the three-way handshake, it does not require elevated privileges. However, because Nmap has to wait for the connection to complete before the API will return the status of the connection, a Connect scan takes much longer to complete than a SYN scan. There might be times when we need to specifically perform a Connect scan, for example, when scanning through certain types of proxies. We use the -S option to start a Connect scan. Next, we'll move on to UDP scanning. UDP scanning. When performing a UDP scan, Nmap will use a combination of two different methods to determine if a port is open or closed. For most ports, it will use the standard ICMP port unreachable method described earlier by sending an empty packet to a given port. However, for common ports such as port 161 that's used by SNMP, it will send a protocol-specific SNMP packet in an attempt to get a response from the application that's bound to that port. To perform a UDP scan, the -S option is used and sudo is required to access raw sockets. The UDP scan can also be used in conjunction with a TCP SYN scan to build a more complete picture of our target. In the next section, we'll explore techniques for handling larger networks or networks with traffic constraints. Network sweeping. To deal with large volumes of hosts or to otherwise try to conserve network traffic, we can attempt to probe targets using network sweeping techniques, in which we begin with broad scans and use more specific scans against hosts of interest. When performing a network sweep with Nmap using the -SN option, the host discovery process consists of more than just sending an ICMP echo request. Several other probes are used in addition to the ICMP request. Nmap also sends a TCP SYN packet to port 443, a TCP ACK packet to port 80, and an ICMP timestamp request to verify if a host is available or not. Searching for live machines using the grep command on a standard Nmap output can be cumbersome. Instead, let's use Nmap's grepable output parameter -O to save these results into a format that's easier to manage. Now we can easily grep the text file for machines that are up. We can also sweep for specific TCP or UDP ports across the network, probing for common services and ports in an attempt to locate systems that may be useful or otherwise have known vulnerabilities. In this scan, we'll look for TCP port 80. This scan tends to be more accurate than a ping sweep. Now we can quickly get a list of IP addresses that have TCP port 80 open. To To save time and network resources, we can also scan multiple IPs, probing for a short list of common ports. For example, let's conduct a TCP Connect scan for the top 20 TCP ports with the Top Ports option, and enable OS version detection, script scanning, and traceroute with -A. The top 20 ports are determined by the Nmap services file. This file uses a simple format of 3 white space separated columns. The first is the name of the service. The second contains the port number and protocol, and the third, the port frequency. Everything after the third column is ignored, but is typically used for comments. The port frequency is based on how often the port was found open during research scans of the Internet. At this point, we could conduct a more exhaustive scan against individual machines that are service-rich or otherwise interesting. There are many different ways we can be creative with our scanning to conserve bandwidth or lower our profile. OS fingerprinting. Nmap has a built-in feature called OS fingerprinting that attempts to guess the target's operating system by inspecting returned packets. This is possible because operating systems often have slightly different implementations of the TCP/IP stack, and these slight variances create a fingerprint that Nmap can often identify. Nmap will inspect the traffic received from a target machine and attempt to match the fingerprint to a known list. The OS fingerprinting option can be enabled with the -O option. The response suggests that the underlying operating system of this target is either Windows 7 or Windows 2008 R2. Note that OS fingerprinting is not always 100% accurate, but a best guess attempt. Consider a more careful examination of the target to confirm an OS fingerprint scan. Banner grabbing and service enumeration. We can identify services running on specific ports by inspecting service banners and running various OS and service enumeration scripts against the target. Nmap's -S option probes open ports to determine service and version information. Keep in mind that banners can be modified by system administrators. As such, these can be intentionally set to fake service names in order to mislead a potential attacker. Nmap Scripting Engine, NSE. The Nmap scripting engine is used to launch user-created scripts in order to automate various scanning tasks. These scripts perform a broad range of functions, including DNS enumeration, brute force attacks, and even vulnerability identification. NSE scripts are located in the user share nmap scripts directory. Let's try out a few NSE scripts to see how they work. The SMB OS discovery script attempts to connect to the SMB service on a target system and determine its operating system. Another useful and self-explanatory NSE script is DNS Zone Transfer. To view more information about a script, we can use the Script Help option. This option displays a description of the script and a URL where we can find more in-depth information, such as script arguments and usage examples. For times when internet access is not available, much of this information can also be found in the NSE script file itself. Take time to explore the various NSE scripts, as many of them are helpful and time-saving. Mass scan. Mass scan can scan the entire internet in about 6 minutes, transmitting an astounding 10 million packets per second. While it was originally designed to scan the entire internet, it can easily handle a Class A or B subnet, which is a more suitable target range during a penetration test. Mass scan is not installed on Kali by default. It must be installed using apt install. Since mass scan implements a custom TCP/IP stack and requires access to raw sockets, we must run it as sudo. To try mass scan on a Class C subnet in the PWK internal lab network, we can use the following example. However, this is presented as an example only. Do not run this within the lab. We'll use the rate option to specify the desired rate of packet transmission, -E to specify the raw network interface to use, which is our VPN interface in this example, and router IP to specify the IP address for the appropriate gateway. Within a few seconds, we have the result of our scan. SMB Enumeration. The security track record of the SMB protocol has been poor for many years due to its complex implementation and open nature. From unauthenticated SMB null sessions in Windows 2000 and XP, to a plethora of SMB bugs and vulnerabilities over the years, SMB has seen its fair share of action. Scanning for the NetBIOS service. The NetBIOS service listens on TCP port 139, as well as several UDP ports. It should be noted that SMB, which listens on TCP port 445, is a separate protocol from NetBIOS. NetBIOS is an independent session layer protocol and service that allows computers on a local network to communicate with each other. While modern implementations of SMB can work without NetBIOS, NetBIOS over TCP is required for backward compatibility and is often enabled together. For this reason, the enumeration of these two services often goes hand in hand. We can use Nmap to easily scan for both ports. There are other, more specialized tools for specifically identifying NetBIOS information, such as NBT scan. The -R option is used to specify the originating UDP port as 137, which is used to query the NetBIOS name service for valid NetBIOS names. NBT scan is very fast and returns a lot of useful information. Nmap SMB NSE Scripts. Nmap contains many useful NSE scripts that can be used to discover and enumerate SMB services. These scripts can be found in the Nmap scripts directory. Here, we find several interesting Nmap SMB NSE scripts that perform various tasks, such as OS discovery and enumeration via SMB. Let's try the SMB OS Discovery module. This particular script identified a potential match for the host operating system. To check for known SMB protocol vulnerabilities, we can invoke one of the SMB vuln NSE scripts. We'll take a look at SMB Vuln MS08067, which uses the script args option to pass arguments to the NSE script. Note that by setting the script argument unsafe equals 1, the script is almost or totally guaranteed to crash a vulnerable system. Needless to say, we should exercise extreme caution when enabling this argument, especially when scanning production systems. In this case, Nmap identifies that the specific SMB service is missing at least one critical patch for MS08067. NFS Enumeration. NFS is a distributed file system protocol that allows a user on a client computer to access files over a computer network as if they were on locally mounted storage. NFS is often used with Unix operating systems and is generally insecure in its implementation. It can be somewhat difficult to set up securely, so it's not uncommon to find NFS shares open to the world. This is quite convenient for us as penetration testers, as we might be able to leverage these shares to collect sensitive information, escalate our privileges, and so forth. Scanning for NFS shares. Both Port Mapper and RPC Bind run on TCP port 111. RPC Bind maps RPC services to the ports on which they listen. RPC processes notify RPC Bind when they start, registering the ports they're listening on and the RPC program numbers they expect to serve. The client system then contacts RPC Bind on the server with a particular RPC program number. The RPC Bind service redirects the client to the proper port number, often TCP port 2049, so it can communicate with the requested service. We can use Nmap to scan for TCP port 111 and run the RPC info NSE script on each server to find services that may have registered with RPC Bind. Next, we'll find out how to make use of this information. Nmap NFS NSE Scripts. Once we find NFS running, we can collect additional information, enumerate NFS services, and discover additional services using NSE scripts found in the Nmap scripts directory. We can run all three of these scripts using a wildcard character in the script name. Let's see what we can uncover with this scan. In this case, the entire home directory is being shared, and we can access it by mounting it on our Kali machine. We'll use mount to do this, along with -o no lock to disable file locking, which is often needed for older NFS servers. Based on this file listing, we can see that there are a few home directories for local users on the remote machine. Digging a bit deeper, we find a file name that catches our attention. Let's try to view it. It appears we do not have permission to view this file. Taking a closer look at the file, we notice that its owner has a UUID of 1014, and the file has read, write, and execute permissions on it. What can we do with this information? Since we have complete access to our Kali machine, we can try to add a local user to it using the add user command. Change its UUID to 1014, SU to that user, and then try accessing the file again. Let's begin by adding a user with the add user command. Based on the output above, we can see that the new user has a UUID of 1001, which is not really what we need. We can change it to 1014 using sed and confirm the change took place. The -I option is used to replace the file in place, and the -E option executes a script. The final argument is the script, which replaces all occurrences of 1001 with 1014. So far, so good. Let's SU to the newly added PWN user, verify that our UUID has indeed changed, and then try accessing that creds file again. We'll use the SU command to change the current login session's owner. Then we'll use ID to display our current user ID. Finally, we'll try to access the file again. Excellent. We can now read the file and make changes to it if we wish. Although the file contents were not what we expected in this particular instance, systems with this level of security are notorious for storing sensitive information in plain text files. Take a moment to think about what else we might have been able to do in this case, from having SSH keys replaced to reading confidential files and so forth. SMTP Enumeration. We can often gather information about a host or network from vulnerable mail servers. The simple mail transport protocol supports several interesting commands, such as verify and expand. A verify request asks the server to verify an email address, while expand asks the server for the membership of a mailing list. These can often be abused to verify existing users on a mail server, which is useful information during a penetration test. Let's check out the verify command in action by using netcat to connect to port 25 on a mail server. Notice how the success and error messages differ. The SMTP server happily verifies that the user exists. This procedure can be used to help guess valid usernames in an automated fashion. This Python script opens a TCP socket, connects to the SMTP server, and issues a verify command for the given username. Let's make this script executable and try it out. Great. Our script is working perfectly. SNMP Enumeration. Over the years, we have found that the simple network management protocol is not well understood by many network administrators. This often results in SNMP misconfigurations, which can result in significant information leakage. SNMP is based on UDP, a simple, stateless protocol, and is therefore susceptible to IP spoofing and replay attacks. In addition, the commonly used SNMP protocols 1, 2, and 2C offer no traffic encryption, meaning that SNMP information and credentials can easily be intercepted over a local network. Traditional SNMP protocols also have weak authentication schemes and are commonly left configured with default public and private community strings. Now, consider that all of the above applies to a protocol which by definition is meant to manage the network. For all of these reasons, SNMP is another one of our favorite enumeration protocols. The SNMP MIB Tree. The SNMP Management Information Base is a database containing information usually related to network management. The database is organized like a tree, where branches represent different organizations or network functions. The leaves of the tree correspond to specific variable values that can be accessed and probed by an external user. For example, these MIB values correspond to specific Microsoft Windows SNMP parameters and contain much more than network-based information. Scanning for SNMP. To scan for open SNMP ports, we can turn once again to Nmap. The -S option is used to perform UDP scanning, and the Open option is used to limit the output to only display open ports. Alternatively, we can use a tool such as 161, which will attempt a brute force attack against a list of IP addresses. First, we need to build text files containing community strings and the IP addresses we wish to scan. We pass our community strings to 161 with the -C option, and the IP addresses to scan with the -I option. Once we find SNMP services, we can start querying them for specific MIB data that might be interesting. Windows SNMP Enumeration example. We can probe and query SNMP values using a tool such as SNMP Walk, provided we at least know the SNMP read-only community string, which in most cases is public. Enumerating the entire MIB tree. Using some of the MIB values we saw earlier, we can attempt to enumerate their corresponding values. This command enumerates the entire MIB tree using -C to specify the community string, -V to specify the SNMP version number, and -T10 to increase the timeout period to 10 seconds. Enumerating Windows users. This example enumerates the users on a Windows system. Enumerating running Windows processes. We can also enumerate the running Windows processes. Enumerating open TCP ports. This example enumerates open TCP ports. Enumerating installed software. Lastly, we can enumerate installed software as follows. Wrapping up. There is never one best tool for any given situation, especially since many tools in Kali Linux overlap in function. It's always best to familiarize yourself with as many tools as possible, learn their nuances, and wherever possible, measure the results to understand what's happening behind the scenes. In some cases, the best tool is the one held by the most experienced practitioner.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.